Let's take a look at derivatives of inverse functions. And in this lesson, we're going to look at how a function is related to its inverse, and we're going to use that to find how the derivative of an inverse function is related to the derivative of the original function. Okay, so buckle up, because this is kind of a lot of sort of making sure that everything makes sense, and then once that all sort of makes sense, you can do the definition. If you get lost in the weeds and you can't quite make sense of it, it is okay to just memorize the definition and work with that. But if you take some time to try and understand where that definition comes from, it will make it easier to remember the definition. Okay, so I have two functions here. I have f of x and f inverse of x. And you'll see that they're graphed here in the dark blue. Now, by definition, the way that f of x and f inverse of x are related is that we swap the x and y values. So for reasons that will become clear later, we're going to actually be mostly looking at the f inverse function and then saying what points on the inverse function correspond back to, or sorry, what points on the original function correspond to the point we care about. So we're looking at a specific point here with some value x equaling to a, and the output then is f inverse of a, because again, we're working with the inverse function. So I'm plugging a into the inverse function, and that will give me this point right here. So there's a corresponding point on the original function with an x value of f inverse a and a y value of a, right? Switching the x and y values. Now, if I move slightly on my function, or if I look at my tangent line slope, right, from when we looked at the instantaneous rate of change, that can be looked at as a change in y over a change in x. So that change in y we see right here for my inverse function is p. The change in x for my inverse function is q. So that means that the derivative of f inverse of a is p over q. And that's just because if I make this tinier and tinier and tinier and tinier, it's going to match exactly onto my function. So I'm just saying I don't know what this is yet, but it's some change in y over some change in x. Now, if that gets tiny and tiny and tinier, then that's going to be related to the difference between this point and the one immediately adjacent to it. So the height change will be some change p, the width change will be some change q, and that will go exactly from this known point to this known point. That point is then corresponding to this point right next to here, which means that my p and q change. So what was my change in height on the original function, or on the inverse function, is now my change in width, or change in x on my original function. Likewise, the change in q is now my change in height. So the slope of the original function at this adjacent point is q over p. So notice that the slopes are inverted, but it's not for the same x value, it's for the corresponding values. Now, what is the corresponding value? It's x equals f inverse of a there. So f prime of f inverse of a is q over p. And this is what we're going to need on our next step there. So this point corresponds with a, right? And the slopes correspond with each other. So I kind of walked through that. I know that some of that tracked, some of that didn't. Maybe go back and re-watch it and just kind of track to see, does it make sense how these match and why they're getting flipped where they're getting flipped. Because that will then lead into our next slide here. Okay, the key relationships that we want to note that I talked about on that previous slide is that the x and the y values swap between the function and the inverse function. This also means that the change in x, or the delta x, and the delta y values swap between two corresponding points. So they're not the same, but like if I swap my x and y values, then the delta x and delta y's between two corresponding points also swap. So this means that, as I had said before, the slope, or in other words, the derivative of those two corresponding or related points also invert. The p over q becomes q over p. So again, if I have corresponding points a f inverse of a and f inverse of a, the slopes of those inverse or they flip. So if I combine this all together, the derivative of f inverse at point A, or sorry, f inverse of x, it doesn't need to be at point A, it can be. So the inverse, the derivative of an inverse function, that's going to be equal to 1 over the derivative of the original function, but I can't put x in here because x is pointing to, if we look back, let me pull up red. If I just plugged in x, that would be the same as plugging in a here. And if we look, that's going to be some point way up here, not my corresponding point. So instead of plugging in x, I need to plug in some function that gives me my corresponding point, which we saw was f inverse of x. So if I use f inverse of x to basically transform it to become my corresponding point, then I can plug that into my derivative of my original function, and then I can use that derivative of the original function, flip it over, and that gives me my derivative of the inverse function. So this is the definition. This is what you can just memorize if you didn't quite follow all of the logic. But that's the idea here. And as with kind of everything that we do elsewhere, this is something that you'll see from examples will help make it abundantly clear kind of how it works.